You made it.
Yes.
Okay.
Yeah, it's pretty big. Wait, why does it I'm always yelling. Really loud.
Okay, so here's who I have not checked off yet. Forgive me if I just missed you. Sarah B, Claire, Matt, Manya, Darwin, Jules. Oh, there's Sarah B. Let's see, Jules. Okay, I know what there. Okay, and then Sarah T. Everybody else I got as you're coming in, and it is time to start. Okay, so we spent a bunch of time last time. Oh, I forgot. Sorry, I keep forgetting my mask. Okay, so we spent a bunch of time last time talking about how to parametrize surfaces. Now we're going to start doing stuff with parametrizations, and so I'm going to do this the same way the book does. They have a lovely approach to sort of segueing into how to compute surface area, and we're going to start off by talking about what are called coordinate curves. So here's a parametrization of a surface. Of course, you notice we have position in space as a function of two parameters, just like all the other parametrizations that we created last time. So the observation that the book makes very elegantly is that if you fix T, so T is not allowed to change now. I'm going to nail it down. It's, I don't know, 3, right? It's fixed at 3, no changing. Now it's just stuck at 3. Well, at that point, then we have position as a function of a single remaining actual live parameter. Position as a function of one parameter. That's a curve. Right. So anyway, this is called the S coordinate curve of that surface. Right. So a pretty easy idea, really, if you think about it. And then likewise, by the way, if you do it the other way, if you fix S, keep that rigidly fixed, and note now we have position as a function of just T. And so that's called the T coordinate curve. of that parametrization. Okay. All right. Okay, so a couple of examples, just so we can see what we're talking about here. Now, by the way, I made a choice. I'm deliberately doing something that looks a little sort of weird at first glance. In my generic discussions through this development, I'm going to have my parameters be S and T, but the example that I'm going to carry us through is the sphere, where we're going to parametrize in terms of phi and theta. I think this is actually a good thing. It seems a little weird perhaps, but just keep in mind, there's no law that says the parameters have to be certain variables. In a lot of books, the parameters are U and V, right? So you don't want to get too sort of attached to certain letters of the alphabet. So anyway, this will be a good sort of practice with that. Okay, so that said, we've got position as a function of two parameters, phi and theta. This is, by the way, we talked about this parametrization last time. This is the spherical graph parametrization of the sphere rho equals 1. If you just plug in rho equals 1 to the regular spherical coordinate formulas, you get this. So this gives us the unit sphere. Yeah, okay, so let's play the game. Let's fix now. We're going to fix phi to be pi over 6, right? So phi now fixed at pi over 6. Well, let me just do it like that. And with phi no longer allowed to change, let's think about what happened. Well, phi is stuck at pi over 6, then theta is the only variable that's actually allowed to change anymore. Phi is fixed. And so we consider position as a function of, well, just theta. And with phi equal to pi over 6, as theta changes, we go along like that. This is the theta coordinate curve. Everybody good? So then now, on the other hand, you could fix theta. Fix theta as pi over 4. With theta fixed at pi over 4, right? Well, now phi is our only variable, and as phi, does like that, right? Theta being fixed at pi over 4, then we get our phi coordinate curve. Everybody see what I'm talking about there? Right? Fix one variable, move the other. You get curves through your surface. Okay. All right. So the big idea then is to notice that these coordinate curves are themselves parametric curves. They're literally parametric curves. And good news, we already know a bunch of stuff about parametric curves. Among them, we know that the derivative of a parametric curve is the velocity vector. Right. So now if you think about it, let me come back up here to my picture. If we say, for example, the derivative of, as theta moves along like that, as we move along our theta coordinate curve, the derivative of this parametric curve, you're taking the derivative with respect to, well, of course, the variable. That is the variable because it's the only one that's allowed to change, right? I mean, the whole point of this is we fixed phi as being, stuck at, constant pi over 6. So now looking at this from the point of view of the parametric surface, we're taking a derivative of position where we hold one of the variables constant and we take the derivative with respect to the other. That's a partial derivative. So the derivative of that coordinate curve is a partial derivative of the original parametrization. So partial derivative of the parametrization gives you the derivative of the coordinate curve, which gives you then the velocity of the coordinate curve. And knowing what we know about velocities, I can make a couple of easy observations. In particular, this, x theta, that's the velocity as I move in the theta direction. That's this little, well, anyway, let me just say x theta. I'm just going to say that's the velocity. So that velocity is what you multiply by d theta to get dx. So this is the change in the input. I multiply by the velocity and I get that vector corresponding change in the output. Right, so that's what velocities do. You multiply the velocity times input change, you get correspondingly output change. Everybody on board? Okay. Okay, so then likewise, of course, for the other, so x phi being a velocity, right? That's what you multiply by d phi. Oh, sorry, colors. What you multiply by d phi to get this dx vector. So again, output change is derivative times input change. Okay. All right. Okay, so we actually now kind of have sort of what we need to start talking about surface area, believe it or not. So the big idea then is, in fact, let me just scroll down to where I have the picture already drawn. Big idea is, you know, if we've got some little piece of area in the phi theta plane, and if I want to talk about how much area does that sort of, you know, what does that land on? How much area does that take up in its image on this parametric surface, right? I can compute that area, ds. I can compute it because it's a parallelogram. I know how to compute the areas of parallelograms. The area of a parallelogram is the magnitude of the cross product of the two vectors, and we've already computed these two vectors. That vector right there. There it is, x phi d phi from the previous page. And this vector here, x theta d theta from the previous page. Area is magnitude of the cross product, chapter 1. Oh, maybe math 218. Anyway, somewhere along in there, right? It's certainly long ago. Okay, so we computed that ds. Now, is this the formula we work from in practice? No, not really. Most of the time, not. There's a nice simplification that we can do here. And the nice simplification is to observe that I've got a couple of scalars in here, and scalars will just factor right out. The d phi and the d theta, just factor them right on out of the cross product, factor them right on out of the magnitude. And so with them pulled out, even better news then, let me sort of, I got a bit of a mess going here. What I've got now then is that having started with d phi d theta as sort of the input area, note that what I factored out is that d phi d theta. And keeping in mind that what I was computing was ds, right? So I was computing the output area. I see now that it's a multiple of the input area. And so what I've inadvertently happened upon is that this formula right here is my stretching factor. So it's like change of variables, really. I mean, it's different geometry, therefore different algebra. Yeah. But still, what we've got is we can view output area as being a known computable multiple of input area. And so we're going to be doing pullbacks and stuff like that. Okay. All right. Is everybody with me? Everybody see how the calculation goes? Nice how it all just kind of falls into our lap inadvertently. Okay. All right. So now there's a notational point here. Excuse me. I'm going to zoom out here. We can see better. And the vector whose magnitude is the stretching factor, this thing right here, we're going to give that a name. We're going to call that capital N. It's very convenient to just have a single name for it, so I don't have to constantly be writing down that formula. So this is called the parametrized normal vector. Oh, correction, this is what I like to call it, the parametrized normal vector. The book calls this, oh, I'm going to pick on the book again. The book's not here to defend themselves, but that's the luxury of teaching a class. The book calls this the standard normal vector. What I don't like about that is this thing depends heavily on the parametrization. It's a peculiarity of the parametrization. I don't know if I would want to call that standard. To me, standard suggests something absolute. And this is not. This is very heavily dependent on the parametrization. You can see in the formula, it's literally derivatives of the parametrization with respect to the variables you're using for the parametrization. It's all about the parametrization. So anyway, heads up, the book uses the word standard. I'm going to be calling it the parametrized unit normal. And so with that, then our formula for the stretching factor, it gets a little bit easier to write down that area stretch. It's just the magnitude of capital N. Just keep in mind what capital N is. Capital N is the cross product of the partials. Is that okay? Everybody good? Yeah.
So we're computing the surface area, but what does the surface area represent in this case?
It's literally the surface area of the sphere.
Oh,
Right. So yeah. So if you, I mean, so what I've gotten the example anyway that I'm working off of is the sphere is parametrized by phi and theta. Right now, we all know the formula from high school geometry for the area of the sphere, but where'd that come from? See what I mean? And there's different ways, of course, to compute that surface area, but I'm presuming here that we don't previously have that formula. Yeah. Yeah. Good question. Anybody else? All righty, so we are in business. We know how to compute surface areas of, well, correction. We know how to compute surface areas of parametrized curves. Notice though, that again, this formula, it depends on the parameterization, or pulling it back a little bit more. It depends on having a parameterization in the first place. So last class, I made the observation that we're going to do some cool things in this chapter, but a lot of it's going to require having a parametrization. So for example, right, we wouldn't be able to make this argument without having a parametrization in the first place. So being able to create parametrizations is a good thing. All righty. Let's see here. Yeah, so let's finish this up. Let's actually compute the area of the unit sphere. So all I'm going to do in this calculation down here is I'm going to execute, pretty much this formula right here. That pieces of area are, well, it's magnitude of the cross product of the partials, d phi d theta. So I'm going to start by, getting my parameterization, taking the partials, taking the cross product, then computing the magnitude, and then you have somewhere to go. So here we go. There's my parameterization. You compute the partials. Now I'm going to gloss over the algebra. Y'all are good at computing partial derivatives at this point. Make sure that you're proficient, quickly, reliably, etc., in computing those partial derivatives. You then take their cross product. Now, again, it's just algebra, but make sure that you can do this. Yeah, taking a cross product of two vectors, especially when the formulas are a little annoying, right? I want to make sure you keep it straight and don't accidentally lose a minus sign and stuff like that. It's easy to mess that up. So you want to make sure, again, Math 218 flashbacks and all that, but make sure that you are, reliable and proficient with computing cross products. And then that cross product, you got to compute the magnitude. And so again, dot, dot, dot. So there's algebra in there, and it's not that bad, by the way. It looks horrendous, but the Pythagorean identity kicks in, if I remember correctly, 3 times. This unattractive looking vector, by its magnitude, it turns out really nice. The magnitude's just sine phi, which is cool. So again, make sure you can do that as well. Okay, so how do you all feel about it? See what the process is? Again, you take a parameterization, you take the partials, you take the cross product, you compute the magnitude. That is your stretching factor. And with the stretching factor, again, it's kind of all over. What's the total surface area of the sphere? The area of the sphere, I chop up into little pieces. Total area is the sum of the little pieces of area. Each little piece of area is stretching factor times d phi d theta. So that's the pullback, just like in change of variables. And we just got through computing this stretching factor. Missed. There it is. There's that stretching factor. And you see, in fact, what we have is just a double integral, double iterated integral even. And so, you know, pretty easy double integral as far as that goes. And make sure you can do that, right? And we got our old familiar answer, 4 pi. Everybody okay? What do you think? Okay. All righty. So just a quick summary of what we've constructed here, and this is, you know, sort of, you know, in general, we've been looking at the specific example of the sphere, but all together, if you have a parametrization, right, then you can form these coordinate curves. When you have the coordinate curves, you can talk about their velocities. When you have their velocities, you can talk about these little edge vectors for the ds. Once you have those, you can compute the area ds. Oh, whoops. You can compute this area ds. Oh, come on, colors. Compute that area ds. And again, what it all boils down to is the cross product of the partials is your stretching factor. Oh, excuse me, as that's the vector whose magnitude is your stretching factor. Yeah, there you go. And the one additional thing that I put on this page, just so it's going to turn out to be useful later. Right now, not so much, but I just happened to point out that when you compute this cross product, notice that the first coordinate of the cross product being, you know, that times minus that times that happens to be exactly that little determinant. Isn't that interesting? That just, what are the odds? It just happened to, you know, I mean, but it is in fact coincidentally a little determinant. So it's you might call that a notational convenience if you want to, you know, make note of that. Now feel free. Okay, do heads up though, in this little observation about these three determinants, a lot of people forget that there is a notorious little minus sign in there. And with that in mind, these two variables in here, that's z and x. The order matters, right? Because it's a determinant. If you switch the two variables in the numerator, you're effectively switching the two columns of the resulting matrix you're taking a determinant of. And so the order matters, and it has to be z comma x. Cannot be x comma z, or you'll be off by a minus sign. So anyway, just a heads up. I will notice that this is actually kind of a better pattern, really. Let me focus in here. It's like you're then kind of going in order around sort of, if you will, colors, X, Y, Z. It's kind of like you're kind of going through there. So Y and Z, Z and X, and then X and Y. So it's like you're going sort of clockwise around that little circle. Arguably, this is a more consistent pattern, really, than, you know, if you got it the other way, you could say, well, it's alphabetical order. Who cares about alphabetical order? Right? This is really more of an actual pattern for your consideration. Okay. Okay. So we know how to compute surface areas, parametrize it. Here's your stretching factor, pull back just like change of variables. Now, I will point out one special case. It is kind of neato, and this is a story that comes up I'll say often. I don't want to say usually. I think it would be an overstatement to say usually, but often the surface that you are dealing with is a graph. If the surface you are dealing with is a graph, we know what our parametrization is going to look like. We're going to use the graph parametrization because, oh my gosh, that's so convenient, right? And I should make the point, this is if this is a rectangular graph, specifically, rectangular graph. Then our graph parametrization looks like this, and that just guarantees then that our partials are going to look like that. And crank it out, you can guarantee that your capital N, your parametrized normal is going to be exactly that, which means that the magnitude is going to be exactly this. So you can save yourself a little bit of trouble and just make the observation that well, as long as you actually are dealing with a rectangular graph, here's the formula for the stretching factor. You can just memorize that formula. And it's pretty nice to save yourself. I mean, it saves you two partial derivatives, right? A cross product. All right, that is actually kind of nice. And then an easy magnitude formula, but still a little bit of streamlining. What I would caution you on this is don't fall too much in love with this. A lot of students make the mistake of thinking, oh, hey, there's a pat formula I can just memorize. For one thing, not everything is a rectangular graph. Again, this has got to be a rectangular graph for this formula to work. If you are not using a rectangular graph, and if this is your primary point of view on how to compute surface areas, then you're dead in the water, right? This only works for rectangular graphs. The other thing is sometimes the surface that you're interested in, while it is a rectangular graph, is really better viewed other ways. So we have already got, in fact, an example of this. So if we look at this example here, and suppose I was looking at the upper hemisphere. Instead of the full sphere, right? If this is what we were looking at, it's a graph. It's a rectangular graph, and you could write down, z equals square root of 1 minus x squared minus y squared, and you could do all that partial derivative stuff that on the next page that we were just looking at, and the algebra will be quite a bit worse than what we're looking at here, right? So just because it is a rectangular graph doesn't mean you should view it as a rectangular graph. Spherical coordinates is a really natural choice when you're dealing with, in fact, a sphere, right? So don't rely too heavily on this. Yes?
When you say rectangular graph, you mean rectangular coordinates?
Yeah. I mean, one of the rectangular coordinates is a function of the other two rectangular coordinates. Yeah. That's right. So if you wanted to have x be a function of y and z, then you could, by analogy, it's exactly the analogous formula. Yeah, totally. So I urge you to view this as a kind of an afterthought, and just in case. But don't let this make decisions for you, and don't choose, oh, I'm gonna lean heavily on graphs for surface areas, because it's a bad strategic plan. Okay. All right. Real quick application though, I do want to show you. I think this is fun. Notice that this bit right. Oh gosh. Sorry. This bit right in here is exactly magnitude of the gradient squared, which is steepness squared. So what this tells us is that, again, if you're looking at a rectangular graph, then your stretching factor depends only on how steep the surface is, how steep that graph is. So one situation where this can be useful is, let's suppose you are looking at the roof of a house. Right now, the roof of a house, most houses anyway, I don't know, my house and most houses that I see, the roof is not just two pieces, that go up and meet in the middle. There's various different faces, and the footprint of the house is kind of, well, the garage juts out, or there's the sunroom in the back, or whatever, right? And so the roof has got many faces, 6, 8, 10 different faces that are sort of all triangular and stuff. And so you could take the point of view of, oh gosh, well, that would be, how would you compute the surface area of the roof? Suppose you're getting your roof done. This is the kind of thing homeowners have to worry about, right? That's very expensive to get a roof done. Suppose you want to check the math and make sure they're not charging you too much for roof shingles. Again, very expensive. Well, one way to do it would be to identify all the lengths up there and figure out the dimensions of each and every one of those triangles, and then deal with a very difficult geometry problem of having a bunch of triangles. None of them are right triangles. And so tedious. The clever move is to notice that when they design houses, they arrange it to where the steepness of the roof in all of those faces, the steepness is usually the same. There's probably a few exceptions, you know, hear that, but most of the faces in almost every house, same steepness, which means that when you're looking at the roof of a house, your area stretching factor is a constant. Which means that computing the surface area of the roof up there, all these different faces and everything, it's just this multiple of the footprint area of the house, which is a much easier calculation. So I think that's a neat observation. Okay, questions? All right. Okay, moving along. We're going to generalize this idea. Now we just got through talking about surface area. Now we're going to talk about a surface integral. And this is sort of an extension of an idea that we've done a bunch of different times. It's chop it up, add it up. We've done chop it up, add it up on intervals, single variable calculus. We've done chop it up, add it up on two-dimensional regions in R2, three-dimensional solids in R3. And we've done chop it up, add it up on a curve in space, right? A different kind of Riemann sum, but look, we chop it up into little pieces. Look at the question you're interested in on each little piece and then add them all up. It's same idea in all four of those cases. Here's version number 5. If you have some surface here in space, again, dimensionally awkward, it's a two-dimensional thing. It lives in a three-dimensional world. I can't talk about a triple integral to compute, let's say the mass or whatever of that surface. It's not a double integral either exactly though, because it lives in three-dimensional space. So what do? Well, I just define a new kind of Riemann sum. And I just say, look, whatever it is that I'm interested in computing, maybe I'm interested in computing mass. All right. Well, then there's a corresponding notion of density. Namely, color choices, sorry. If you're interested in mass, you'd be looking at mass per unit area that you would then multiply by area. If you've got ants crawling over your surface and you're going to compute total population of ants, well, then ants is going to be ants per unit area times area. So again, there's a population density in that case. Ultimately, though, chop it up, add it up. I don't want to get distracted by the formalities of it all, but this is what we need to sort of take away from it. So we're adding up over two indices. So I'm going to use double integral notation because it is a two-dimensional Riemann sum. It's a two-index Riemann sum. And as usual, I'm going to shorthand the little pieces of area, call them a differential. And this notation here is actually pretty plausible. And then of course, the domain is whatever surface you're chopping up in the first place. So I want to assert that this is really I'll call it a kind of a shameless ripoff of the idea of a scalar line integral. It's the scalar line integral, except it's on a surface instead of a curve, but same idea. And so we are also going to rip off the terminology. And this is a scalar surface integral because it's on a surface. What do you think? Now, with the understanding, the looming question of, yeah, but how do I compute these things? Oh, we'll get there, right? But just in terms of having a strategy of chop it up, add it up, everybody happy with that part? Right. By the way, just like with line integrals, there's this sort of question of why do we need to specify that this is a scalar surface integral? And it's because there's going to be another version of surface integrals that we'll see pretty soon, possibly today, we'll see. But you can probably guess, we're going to see something called a vector surface integral coming up soon. So just like with line integrals, we had scalar line integrals and vector line integrals, analogous here. But for the moment, our integrand is a scalar, our differentials are scalars, so scalar surface integral. Okay. All right, and I claim we actually kind of already know how to compute these things, because what we really need in order to be able to compute these things is I need to be able to do a pullback on my surface. Well, I already know how to parametrize surfaces. And I'm also going to need to know how to understand ds. Oh, good news. We already know how to understand ds. We've already talked about computing surface areas, and this ds representing area. Oh, I've got it right here. Representing area there on my parametrized surface. It's the same ds that we were talking about a couple minutes ago. So it's really just kind of a matter of kind of writing down what we already know. And here goes. So let's see here. Yeah, we're interested in computing some line integral. I mean, why, by the way? Maybe we're computing the mass on our surface. F represents surface density, or mass per unit area density. Or maybe we're counting ants, and that's population density. Whatever. If you're interested in computing this scalar line or scalar surface integral, then ds is stretching factor times ds dt, or whatever your parameters are. Right? The ds dt being again, from your parameterization. So whatever the parameters are for your parameterization. And it's the same exact stretching factor here. Magnitude of capital N still xs cross xt. So, same. Again, it turns out we already inadvertently knew how to compute these scalar surface integrals. Okay, is everybody happy? Before I do an example, does anyone have any questions going in? All right, so I'm going to rip off an idea that I did with scalar line integrals, and I'm going to look at one object and ask a bunch of different questions about it. We're going to compute the mass, the center of mass, various different coordinates, 2 different coordinates of the center of mass, moment of inertia around some arbitrary axis, etc. And we're going to do all these calculations at the same time because, well, they're all of the same mass distributed over the same surface by way of the same density with the same parameterization. The only thing different is the Riemann sum that we're going to start with, but all the specifics of the calculation here are the same, right? Now, you'll notice further, I'm looking at a part of the unit sphere, and so I can parametrize with the same exact parametrization that we already looked at. And so conveniently, I get to cite the same result that we already computed, back in when we were looking at surface area. I already know that my stretching factor is sine phi, so that comes from this example right here. So same parametrization, so same stretching factor. Everybody remember this? Everybody comfortable with my assertion here? Let's see here, here we go. Okay, so yeah, we're going to parallel compute now 4 different things. So let's see, I guess I better zoom out and fit all this on. Yeah, here we go. So we're going to compute mass. Great. Mass is chop it up, add it up. Sum of a bunch of little pieces of mass. Moment of inertia, integral r squared dm. Details to follow. The x coordinate of the centroid, the z coordinate of the centroid. Again, we've got formulas for these. So notice in all cases, though, I mean the work, most of the work is kind of hidden inside of here. Of what is this dm and how do I deal with it? So let's deal with that. Well, okay, so dm, mass is density times size. Note same move in all four of these calculations. Doesn't really matter what we're computing. dm is density times ds because we're on a surface. And by the way, notice density is z in all of these calculations because, well, it's the same density on the same surface. Everything's the same, so density is still z. Let's see here. Again, we've already observed that our stretching factor is sine phi. Right? So with that in mind, all this is the same. The spacing is a little different, but all of this is the same in all four of these calculations. ds is sine phi d phi d theta because sine phi is our stretching factor. Everybody good? No, then we've got various different things to plug in. Let's see here. I guess we'd better observe that since we're rotating around the z-axis, you know, for that moment of inertia calculation, going around the z-axis, our r is square root of x squared plus y squared. So r squared is x squared plus y squared. That's, you know, sort of a peculiarity of that calculation. And everything else is just kind of a matter of plugging things in. I mean, directly from our parametrization, z is cosine phi. Z being our density. Same parametrization, same plug-in. Let's see, we're also from our parametrization, x is sine phi cosine theta. Oh, let's see here, z is cosine phi. X squared plus y squared, again, from our parameterization, it's a matter of plugging in. And we're in business. So 4 separate things. You know, you could think of this as 4 separate examples, I guess, but it's really one example more. I mean, in terms of most, I'll say these 4 separate examples overlap in most of the ideas that go into working them. Everybody see that? Yeah.
Should we be able to evaluate these, or would we just be actually accept them?
Yeah, I think these are all reasonable. They're trig integrals are a little annoying, but I think they're all reasonable. So make sure that half angle formulas, of course, are one of the big tricks. Double angle formulas are really useful sometimes. And yeah, you know, the occasional substitution, Pythagorean trickery is always a good thing. But yeah, I think these are all, they all look pretty doable. Yep. Anybody else? Okay. Let's see. The trouble with this full screen mode is then I don't have a clock to look at. Oh, okay, I've got 10 minutes. Good deal. Okay. All right. So that was scalar surface integrals. Now I want to flashback now to long ago, back in chapter 3, we talked about this thing called flux. So y'all may recall, I drew a picture much like this one. In fact, I think I may have literally copied that picture. So y'all may recall this picture. And the idea of flux is that it's the answer to various questions that we might be interested in, such as suppose my vector field represents the velocity of a fluid, like maybe the velocity of air in this room or something like that. And I want to know how much volume per unit time is passing through some surface. Well, flux is the answer to that question. The F dot N times the area. On the other hand, kind of a different question now. Suppose I want to know the mass of the fluid that's passing through my surface. Well, then I need my vector field to be adjusted. I've got to have a factor of density thrown in there. But anyway, point being, depending on your physical setup and your physical interest, this expression here, flux, tells you in some sense how much fluid's passing through your surface. And details, of course, have to be, appropriate. So we're actually interested in then for, pick your application, but we're interested in this formula here, F dot N times area, called flux. So here's the problem with what we've done previously on this. This does assume that your vector field is constant, and this also assumes that your area is actually flat. So what we're going to do now is consider what happens when one or possibly both of these fails, right? What if your vector field is not constant? What if your surface maybe is curved? Either or, usually both. Right? Then what? You can't just draw this picture, because this picture makes lots of assumptions that are no longer valid. So we've got a chop it up, add it up problem. Right? So here now is a non-flat surface, which I totally could. I mean, I could be fishing and pulling a net behind my boat, right? And well, look at that net's probably not flat, right? The current's probably going to bend that and make it kind of rounded as it gets pulled behind the boat. So, well, chop it up into little pieces. Focus on the little pieces. Each piece is approximately flat. On each little piece, the vector field, now the vector field varies wildly. Let's see here. The vector field is, it's like that there, but it's like this over here, and it's like that over there. I mean, the vector field's wildly not constant, but on a given piece, if I focus my attention just, since I'm looking at just this one little piece, it just doesn't have enough I mean, there's not enough distance between, everything's so close together that field doesn't have time to change very much. And so it's approximately constant. So on each little piece, we can just use the usual formula. It's the usual chop it up, add it up strategy. And we've got some details that we got to write down and some issues to worry about. But this is the big idea of how we're going to create this thing called a vector surface. Pausing before we go on. Okay. All right. So let's see here. Now I do want to switch over to, here's where we had a similar discussion when we were talking about work. And, work, we've got this formula F dot D from chapter 1 and, high school physics classes, possibly even. But this assumes, again, that the vector field's constant and that the displacement is a straight line and everything. And so we chop it up into little pieces where we have approximately straight, approximately constant. Morally, that we're doing the same thing that we did back with and developing what y'all recall turns eventually into vector line integrals. But do remember, there was this issue of orientation. Right? I have to talk about not just a curve, but an oriented curve. I can't talk about the amount of work it takes to drive the road. I need to know, wait a minute, which direction along the road? Do you want me to drive up the mountain? Do you want me to drive down the mountain? Different story. Right? Very different story. Going up versus down. Now, of course, the difference is just a minus sign, but nevertheless, that's a big difference. In terms of, whether you expend a huge amount of energy or whether you recover a huge amount of energy. Right? Okay. So the orientation on a curve, how do we indicate an orientation? Well, you just tell me which way you're going. Effectively, you're indicating it by a tangent vector. The tangent vector saying which is the right direction. What's the direction we're going here? Okay. Well, there's an analogous story here. If you want to talk about how much fluid is going through your surface, going through which direction, if this is what I consider, if this is what I consider to be the positive direction through the surface, right? Then as I have it drawn, this vector field, well, it would appear we have a positive flux because, well, all the water is going through in the indicated direction, right? But if for whatever reason, if the fluid were going like this instead, well, the fluid's going very different. I mean, it's going the opposite direction of the other one, and the orientation's that way, but the fluid's this way. So this I would want to call a negative flux, indicating that it's going the other way. Does that make sense to everybody? See how it's kind of analogous to line integrals? Okay, so that's all going to flesh out. Point being, though, that we have to indicate, if we're going to talk about flux, that we have to worry about the minus sign of which way is the right way through it. And the way we do this is we note that flux is defined through oriented surfaces specifically. You've got to tell me which way is the positive way if you want me to sort of keep track of which, how much stuff is going through. And we indicate the orientation by way of a normal vector, a unit normal vector. And I'm going to call this the orientation unit normal, because this normal vector here serves the purpose of defining the orientation of my oriented surface. Okay, what do you think? Everybody on board? Does that make sense? Seem reasonable? All right. Okay, so so chop it up, add it up on each little piece. We've got a simple story, again, on each little piece. It's approximately flat, so I can just talk about the surface area. And it's the normal vector is approximately constant, so that's cool. The vector field is approximately constant, and so I can just, use the old formula. Flux is just add up all the little bitty pieces of flux. And so this is something we can just straight up do. Total flux is the sum of all the little pieces of flux. Those little pieces of flux are this. And so grand total, we have now kind of a new kind of an integral. Let me write it like this. Integral f dot n ds. Yeah. Okay, that's just kind of recognizing what we've previously got. Okay, now I am going to pull a little move here. This is kind of like something we did back with vector line integrals. So specifically, I see the n and the ds together here. I'm going to call that the ds vector, because conveniently, this n is telling me about the orientation of my piece of surface. The ds is telling me about the size of the piece of surface. Together, by a direction and a magnitude, these two factors are telling me about my piece of surface, are telling me everything I need to know about my piece of surface itself. And so it makes sense, I think, to give this a name. I call it the ds vector. This is pretty standard. I think our book is using the same notation, if I remember correctly. And so just this is another thing to remember. It's just a notational convenience. The ds vector is the orientation times the area. And just for comparison, note that we did something analogous, with line integrals. The dx vector is the orientation tangent vector times the size in the form of, ds scalar. So same deal, just surfaces instead of curves. And I guess we're out of time, so we will draw a line here, pick up here on Wednesday. See y'all later. Have a good one. And don't forget to let me know if you came in after I did attendance.